Scientists are sitting in silence. Not because there is nothing to say, but because what the James Webb Space Telescope has been sending back from deep space is so far outside everything they thought they knew, that some of them genuinely do not know where to begin. In the last 12 months alone, this telescope has captured images that have forced astronomers to stop, look at each other, and quietly admit that some of the most fundamental textbooks in cosmology may need to be rewritten from scratch. Not updated. Rewritten. This is not a story about beautiful pictures of space. This is a story about a machine that cost $10 billion, looked deep into the universe, and found something that, according to our best understanding of physics, simply should not be there. The James Webb Space Telescope launched on Christmas Day of 2021, and it began full scientific operations in mid-2022. It orbits the Sun at a point called L2, about 1.5 million kilometers from Earth, far enough away to avoid the heat and light interference that limited older telescopes. Its primary mirror measures 5 meters across, coated in gold, and divided into 18 hexagonal segments that unfold like the petals of a flower. It does not see light the way your eye does. It sees infrared, the wavelengths of light that pass through clouds of gas and dust that would block visible light entirely. This means it can see things that have literally never been seen before in the history of science. It can see through the walls of stellar nurseries. It can analyze the chemistry of atmospheres on planets orbiting other stars 40 light-years away. And it can look so deep into the past, so far back in time, that the light it collects left its source when the universe was only a few 100 million years old. Before the James Webb Space Telescope began operations, astronomers had a very clear picture of how the early universe was supposed to work. In the first several 100 million years after the Big Bang, the universe was supposed to be in a kind of infant state. The first galaxies were supposed to be small, dim, irregular, and loosely structured. The materials needed to build large, organized, brilliant galaxies simply had not had enough time to collect and organize. The physics of how matter clumps together under gravity, the equations that govern star formation and galaxy growth, all of these pointed to the same conclusion. The early universe should look young, simple, and relatively dark. What the James Webb Space Telescope found instead stopped researchers cold. When the telescope pointed its instruments toward the most distant reaches of the observable universe, looking back to a time when the universe was only 3% of its current age, it found galaxies. Not small, dim infant galaxies. Massive, bright, fully structured galaxies blazing with star formation. Organized and enormous, containing hundreds of billions of stars each. Galaxies as large and as heavy as our own Milky Way, fully formed, sitting in a universe that was supposed to be far too young and far too simple to produce anything like them. Astronomers have described this discovery using the word that scientists almost never use. They have called it shocking. One researcher stated publicly that finding these galaxies in the early universe was like finding a fully built skyscraper at an archaeological site where you were only expecting to find scattered stones. The structures simply should not be there. The numbers are staggering. Some of the galaxies detected by James Webb are estimated to have masses up to 100 times larger than what our best theoretical models said should be possible at that point in cosmic history. Several of them appear to contain populations of old red stars, meaning that these galaxies had already been forming stars for a long time before the point when Webb caught them. They were already ancient when the universe was in its infancy. Every existing model of galaxy formation struggles to account for this. Some scientists have openly stated that these findings call the entire standard picture of early galaxy formation into question. The data is not a small anomaly at the edge of the error bars. It is a consistent, repeated, undeniable pattern that shows up everywhere the telescope looks. And then the red dots appeared. These little red dots did not behave like normal galaxies. Their light spectra were unusual. Their brightness was unusual. Their size was unusual. They appeared almost exclusively in images of the early universe, present in huge numbers in the first billion years after the Big Bang, and then they simply vanished from the record around 2 billion years in, disappearing as suddenly and completely as if they had been switched off. For 3 years, astronomers debated what they were looking at. By late 2025, a team led by researchers at the University of Texas at Austin had produced what is now considered the strongest evidence yet for a startling answer. These little red dots may be black hole stars. The scientific term is BH stars, and the concept is as unsettling as the name sounds. They are not galaxies in the conventional sense. They may be enormous spheres of superheated gas so dense and so massive that they have supermassive black holes at their very centers. Those black holes are not hiding inside the objects. They are essentially driving them, pulling surrounding matter at incredible rates and converting it into energy and light. The object glows from the outside like a star, powered not by nuclear fusion, but by the raw gravitational hunger of a black hole consuming everything within reach. One particular little red dot catalogued as Glimpse 1175 was studied with the deepest spectrum ever obtained of such an object. The evidence pointed clearly toward this black hole star model. The object is surrounded by a dense cocoon of partially ionized gas, precisely what the model predicts. Researchers at NASA confirmed that the scientific community is increasingly converging on a single explanation. These compact, brilliant, ancient red objects are a completely new class of cosmic object that no previous telescope had the power to detect, and no previous theory had predicted in quite this form. They may hold the answer to one of the deepest unsolved mysteries in cosmology. How did supermassive black holes, objects containing billions of times the mass of our Sun, come to exist at all? The standard model of black hole formation cannot easily explain how they grew so large so quickly. The black hole stars may be the seed, the violent, blazing, consuming origin point of the supermassive black holes that sit at the heart of galaxies today, including our own. But the James Webb Space Telescope has not stopped there. In January of 2026, the telescope turned its instruments toward one of the most famous objects in the known universe, the Helix Nebula. This object sits just 655 light-years from Earth, close by cosmic standards, and it has been observed by astronomers for centuries. When viewed at a distance, it has the shape of a vast eye staring out from the darkness, which is why people have called it the Eye of God for as long as photographs of it have existed. What sits at its center is a white dwarf, the burned-out, cooling remnant of a star that was once much like our own Sun. When that star died, it shed its outer layers in a slow-expanding explosion, creating the glowing rings and pillars of gas that form the nebula we see today. Hubble photographed this object years ago and produced beautiful images that showed the broad structure of the nebula. What James Webb did in January 2026 was something different. It zoomed in using its near-infrared camera. It captured a close-up portion of the Helix Nebula at a level of detail that was simply not possible with any previous instrument. And what it revealed inside those glowing clouds was extraordinary. There are structures in the nebula called comet knots, dense pockets of gas that trail long tails away from the central white dwarf, shaped exactly like comets flying away from a star. There are pillars of gas curving in arcs across the image. There are distinct layers visible with perfect clarity in infrared light that show the transition from the hottest gas near the white dwarf to the coldest molecular gas at the outer edge of the expanding shell. Complex molecules are already beginning to form inside the cooler dust clouds, including the kinds of carbon-bearing molecules that are the building blocks of chemistry as we understand it. Here is why that matters beyond the visual beauty. The Helix Nebula and objects like it across the universe are how the cosmos recycles itself. The material shed by that dying star, the atoms of carbon, oxygen, nitrogen, and silicon drifting outward through space, will eventually become the raw material for new stars and new planets. The molecules forming right now inside those cold dust clouds may one day be incorporated into a world orbiting another star. The James Webb image of the Helix Nebula is not just a picture of a dying star. It is a picture of creation and progress, of the process by which the death of one stellar generation seeds the birth of the next. And it is a picture that shows with a level of clarity that no human being has ever seen before exactly how that process works at the physical level. Scientists looking at this image have noted something else. The structure of the Helix Nebula, the way the expelled material is organized around the white dwarf, gives us a preview of what our own solar system will look like in approximately 5 billion years, when our Sun exhausts its fuel and begins the same process. The James Webb image of the Helix Nebula is a photograph of the future, our future. It is the most detailed picture ever taken of what the Sun will eventually become. Meanwhile, 40 light-years away from us in a star system that has occupied astronomers for nearly a decade, something even more significant may be occurring. The star TRAPPIST-1 is a red dwarf, small and cool, orbited by 7 rocky planets that are all roughly the size of Earth. Several of these planets sit in what astronomers call the habitable zone, the range of distances from the star where temperatures could, in principle, allow liquid water to exist on a planet's surface. If you are looking for life elsewhere in the universe, TRAPPIST-1 is the kind of system you study. And in September of 2025, the James Webb Space Telescope produced results from TRAPPIST-1e, the fourth planet in the system and the one most consistently identified as the best candidate for Earth-like conditions that have the scientific community holding its breath. What Webb found was evidence, tentative but real and documented, of an atmosphere on TRAPPIST-1e. Using its near-infrared spectrograph instrument, the telescope analyzed the light that passes through TRAPPIST-1's outer layers during the moments when the planet crosses in front of its star. The signatures in that light pointed toward a possible atmosphere containing nitrogen and methane. A rocky planet the same size as Earth, 40 light-years away, with an atmosphere showing chemical signatures similar to those of our own world. The research team, drawn from scientists across the United Kingdom, the United States, and India, published their findings in the Astrophysical journal Letters. The results were careful and precise. They ruled out a thick primordial hydrogen atmosphere of the kind a gas giant would have. What they found instead pointed toward a secondary atmosphere, the kind that forms through processes like volcanic outgassing after the planet's initial formation. A secondary atmosphere on a rocky planet in the habitable zone of its star. That is exactly the type of atmosphere that could, in principle, support liquid water on a surface. The researchers noted that additional observations are already planned and underway, with follow-up data expected to provide much clearer answers. No one is claiming that life has been found on TRAPPIST-1e. Scientists are careful about that. But the confirmation that a rocky, Earth-sized planet in the habitable zone of a nearby star has retained a secondary atmosphere is the most significant step toward that question that has ever been made. Every previous step in the search for life beyond Earth has been about identifying the right conditions at a distance. This is the first time the telescope has pointed at a world with the right size, the right location, and potentially the right atmospheric chemistry and found signals that match. Now return to the deeper discoveries, because the implications of what James Webb has found in the early universe go beyond individual objects or individual detections. They point towards something bigger and more unsettling. The universe, as we understood it before James Webb began operating, had a clear story. The Big Bang produced a young, hot, rapidly expanding universe. Over hundreds of millions of years, matter slowly organized under gravity. Small structures formed first, then larger ones. Galaxies assembled gradually. Stars formed in waves. Black holes grew slowly from stellar remnants. This story was built over decades of observation and calculation. It was the foundation of what cosmologists call the standard model of cosmology. And it was supported by enormous amounts of evidence. What James Webb has done in less than 4 years of operation is find exception after exception to that story. The giant galaxies that should not exist in the early universe. The little red dots that appear to be an entirely new class of cosmic object powered by mechanisms we did not predict. Supermassive black holes containing over 1 billion times the mass of the Sun sitting in a universe less than 700 million years old with no clear explanation for how they grew so large so quickly. The standard model does not break under the weight of 1 or 2 anomalies. But the pattern of what James Webb is finding is not 1 or 2 anomalies. It is dozens, accumulating faster than theorists can construct new explanations. Several cosmologists have stated publicly that James Webb is forcing a genuine reckoning in the field. Not a minor adjustment, but a fundamental re-examination of what happened in the first billion years of cosmic history. The equations that govern how matter behaves, how gravity shapes structure, how black holes grow, and how galaxies form are being tested against data they were never designed to face. Some of them are holding, some of them are not. And the process of figuring out which is which, of rebuilding our picture of the early universe from the ground up, using what James Webb is showing us, is already underway in universities and research centers around the world. There is something worth sitting with in all of this. The James Webb Space Telescope was built to answer specific questions. How did the first galaxies form? What do the atmospheres of distant planets look like? What happens inside stellar nurseries and nebulae that visible light cannot penetrate? These were the questions written into its design, and it is answering them every day. It is gathering data, sending back images and spectra, giving astronomers more material to work with than any previous instrument in history. But the deeper thing that James Webb is doing, The thing that makes this moment in science genuinely extraordinary is that it is not just answering the questions we asked. It is revealing that some of the questions themselves were based on assumptions that may not be correct. It is showing us that the universe in its earliest stages behaved in ways that our models did not fully predict. It is finding objects that fit none of our categories. It is detecting signals from worlds that push our understanding of habitability to its current limits. It is photographing the remains of dying stars with such precision that we can watch the chemistry of the next generation of solar systems beginning to form in real time. The Helix Nebula, that ancient eye staring out of the darkness 655 light-years away, contains within its cooling clouds of gas the atoms that may one day become an ocean on a world we have not yet discovered. The little red dots blazing in the ancient universe may be the violent consuming birthplace of the black holes that now anchor galaxies across the cosmos, including the one at the center of our own. The faint signals threading through the starlight of TRAPPIST-1 may be the first whisper of chemistry on a world that is not Earth. James Webb was built to look at the universe. What it is actually doing is making us look at ourselves differently. At where we are, at what we are made of, at how unlikely or perhaps how inevitable our existence actually is inside a cosmos that is older and stranger and more complex than we had previously allowed ourselves to understand. The silence from some scientists is not the silence of people who have nothing to say. It is the silence of people who are carefully choosing their words. Because the data coming back from a gold-coated mirror orbiting the sun 1.5 million kilometers from Earth is telling a story that is going to take years to fully tell. And every new image, every new spectrum, every new detection is adding another chapter to that story. A story about the beginning of everything and about the conditions for life. About the structure of time and matter and gravity at scales that dwarf anything a human mind can intuitively grasp. The telescope is still looking. The data is still coming. And the picture it is assembling of the universe we live in is more astonishing, more complex, and in certain ways far more humbling than anything we imagined when we first pointed it at the sky.